Well, there we go. Well, thank you very much for the invitation, Brian. Brian, of course, being, we were co-workers for a few years back working for Market. So anyway, I am here today to provide the perspective of what a private sector person, myself, would be interested in running NWP in the cloud for. And so the title is Challenges and Successes. I am the presenter, but I will easily say that I'm not the only one that contributed to this presentation. There's a list of co-authors below, all of whom are my fellow Maxar folk. I'm also convinced that unwittingly I have probably incorporated some thoughts from conversations I've had with others in the past. So there may well be an unnamed co-author or two. I have a feeling that like some of Chris Harrop's ideas are probably in this in some way, as are others from the folks I've known over the years. Now, being that this is a private sector-based presentation, disclaimer at the start, I mean, all those folks did help me with the presentation, all my fellow Maxar folks, but the opinions that are going to be presented today are mine. They're not any sort of Maxar corporate policy. And so they are attributable to me. So I guess I get the credit or the blame, depending on one's point of view. So having not actually ever given a keynote address before, when Brian Flint approached me about it, I asked, well, you know, what would you be interested in hearing a little bit more about? And I don't believe that he realized that a sort of 6-line response email was going to wind up being the framework of this talk, but here we are. So there were things that I was asked about. Why would a private sector company go out and use cloud computing for NWP? And there's these 6 different questions. The first being, well, why would we use the cloud versus just buying our own cluster or some other on-site hardware? The second one, which I'm very keen to share what I can on, is the cloud really that much less expensive? The third, on the software side, there's certainly things to address there, which I will. Is performance that much of a concern? Is accuracy more important? And then the 6th question that Brian put to me is, are companies adding any sort of secret sauce to try and make stuff better? I like that he used those quotes because it gives a little bit of wiggle room to comment on things a little more broadly. So I wasn't sure about the full scope of and background of all the folks listening in. So even before I get to the 6 questions that Brian posed to me, I thought I would at least do, you know, what it is to do HPC in the cloud. Now, from, you know, my days way back at Penn State at the turn of the century on to now, you know, I'd always thought of high performance computing as being some sort of cluster computer, you know, Cheyenne or the Theia, Gaia, Noah, you know what I'm talking about. But in the cloud, it is not that at all. There is no on-premises thing in the basement of the building that is, you know, this set of nodes that are all connected to each other that are there, you know, in perpetuity. Well, not perpetuity, they don't only last a few years. Effectively, HPC in the cloud is achieved by building your cluster whenever you want or need it. If you go to one of the 3, there's 3 really main vendors that I think of in cloud computing: the Amazon folks, AWS, Google, and then Microsoft's Azure. And if you go to any of their websites, because there's a lot there that you can learn about HPC and cloud computing from, when you want to go and get yourself a cluster to run things on, there's a whole bunch of different types of things you can do to customize it a great deal. The first is just going out and getting your compute nodes. And when you go out and get them, there are many, many different types. I mean, I've messed around with some Skylakes. Oh, actually, it's even broader than that. I mean, there are some that have accelerators, some that are, you know, slower gigahertz clock speed, some that are faster. Varying types of nodes are available. Varying amounts of cores per node are available. I mean, in the case of the Skylake chip, I think you can get maybe even up to 48 compute cores on a node, and then lesser amounts on that as well. Also varying amounts of memory. I mean, you can have the same basic processor, but they might have more or less memory on a thing. One thing that's kind of interesting on this list of the compute nodes that you would use in a cluster, varying physical locations. They've got these, you know, I don't know if you've ever driven by one, sort of server farm things spread out around the nation, around the world, really. And the reason that I wanted to mention that is that if you think about, you know, doing high performance computing, the interconnect is important. And so you would certainly want to pick a selection of nodes that is in the same physical location, obviously to make things as well connected as possible. And in all of the above, and this is something that of course is very important to the private sector, is varying costs. Certainly if I pay for using the latest chipset in my compute cores, well, that will be more expensive than if I use, maybe 2 or 3 year old nodes, or all of the rest, the cores per node, the amount of memory, and even the locations. It tends to be the case that compute, if it's coming out of California, it's more pricey than the other places. It is true that not only do you have a lot of flexibility in the compute nodes that you get, but you have flexibility in the interconnect. That's getting better all the time, but it could be just TCP if you did not want to pay for more. When you make your cluster, the file system is also something that is variable. What you connect to those compute nodes, you can basically tailor its size and speed as you wish. And so all of this means that, yes, like the cluster that I use today, if I want to run the model today, can be absolutely a different thing than the one I used yesterday. And that's something that the cloud offers that an on-premises old school, I know I shouldn't say old school, traditional system would allow. So why, this is now getting to Brian's list of questions, why use the cloud versus on-site dedicated hardware? And I'm going to try and do this in as, it's a private sector thing, so there's some proprietary information in here that I need to steer clear of, but I'm going to do it as well as I can. So if any company is making something to sell a product of any sort to put on the market, the absolute goal is to make something that a lot of people want to buy, or at least enough, that you can sell for more money than it costs for you to make. Now, one of the things that we have found out at Maxar, and other people know this too, folks in the energy sector, et cetera, but there's a lot of people when it comes to different commodities markets, agriculture, energy, they make decisions, trading decisions, like how much to bid on a barrel of crude oil or some such thing, based on what the traditional sources of weather information have to say. And certainly GFS and IFS, the Euro and the NCEP models, really have a strong push on which way the market moves. And there are absolutely customers out there that would just love to know what those models are going to predict, a little bit before everybody else finds out. And so if you could just run FV3 faster than NOAA, there are folks that would be very interested in doing that. But from our point of view, in order to run FV3 GFS faster than NOAA, you have to use more compute than NOAA itself does. And the idea of then buying and putting in the basement a supercomputer cluster that is just bigger than the one that they run in operations that's just absolutely cost prohibitive. Again, I can't get into the dollars and cents, but you could imagine, most folks have an idea of what an NCEP computer costs, and we would not generate that kind of income ourselves. And so cloud computing resources, since we only pay for what we need, allows us to have that be a profitable situation, that we can compute something in a timely manner and at a cost that works for us. Again, not incurring the cost of owning our own cluster. So for about a year now, Maxar has run and continues, it's going to start, in about an hour from now, something we call the Cirrus program. Basically what it is that we run FE3. The charts on the right are just our run on the top and NCEPs on the bottom. This is from, these slides were from the UFS workshop back in July. And so the success of the program does rely on us being able to produce FE3 faster than NOAA, but of course it has to be the same thing because, well, not identical, of course, but close enough that folks could say, oh, the GFS, the FE3, as you wish, is going to predict a hurricane in 10 days. And so folks are going to get worried about oil rigs in the Gulf of Mexico or some such thing. And so the idea is that folks would know that in advance. And so the success of our program relies on Maxar being able to run our application faster than NOAA does. And the only way that we were able to do this in a cost-effective manner is, well, we worked in our case with the Amazon group, AWS. That's our cloud computing. I mentioned there are three. AWS is the one that we partnered up with to develop our environment, to be as cost-effective and scalable as we can. There's a collection of tools there listed that we use to get it done. EC2, that's effectively the compute capability. Parallel cluster, that's the software that allows you to do this creation of a cloud cluster with relative ease. EFA, that's the Elastic Fabric Adapter, the interconnect between nodes, which is certainly faster than TCP. Obviously, we need a file system, FSX for Lustre. All of these things we use together to set up our system for allowing us to run FE3 at a great speed. The first thing that we, of course, had to do to get this going was to go get the source code from NOAA, which I guess now, since it's going to move towards UFS, will be in wherever the UFS will be held. But we had to get it, and we basically had to rework it so that it would be able to function in the cloud. We certainly had to recompile it, and I did that. And every now and then you run into something that's a derived type. One of the issues here is that in doing the recompilation, I mean, it's not likely that we got the exact same compiler that others were used. It's clear that we probably have different hardware. And so there's going to be things that we're going to need to redo to get it to run. And yeah, I definitely remember finding some derived types that needed to be, well, not commented out, but just sort of sorted out so that you could compile it. Obviously, there's a workflow that we inherited where all the directories and path structures had to be reworked. And then after that, as many of you are aware, you do want some bit of optimization for the hardware you're running on. And the one thing that I definitely did a bit on, the NCEP computers, the one that they use in operation, they're not 36 cores per node. And so since ours are, there's a bit of a rework of the layout. For those familiar with FE3, there's 6 sides, this cube sphere grid, and each one you break up into patches. And there's just certain configurations that are more appropriate for 36 cores per node. I wanted to comment on all of those because, of course, if you changed what cluster you use, you're going to have to do a lot of that stuff again. Maybe not the full-out recompile, but certainly, Skylake, for example, you can use AVX 512 in the compiler, the list of compiler options. Whereas if you switch to a different chip, you'd have to recompile to accommodate that. And if you switch your cores per node, the layout that you think is most optimal will also have to change. So did the refactor, which was not insignificant, but clearly not insurmountable. And then the entire workflow, and when I say entire, it's not just, download model, run model, send output, wherever. It's the whole thing. It's the process of actually from nothing, spinning up the cluster with all the nodes you want and the interconnect that you want and the file system you want. So you spin it up and spin it down each day. And that's, of course, very significant. It's that only acquiring the amount of compute that you really need. The execution workflow is automated. There's a series of step and lambda functions with notifications. Certainly we get a word back if there's a node failure or if anything goes wrong along the way, because obviously we have to keep an eye on this thing. And there are ways that you can do this in as automated a way as you can. I mean, there's CloudFormation stacks, there's the code pipeline, there's these things that are available so that if you do have something that you need to change or improve, it's not quite as onerous a task. So this is effectively how our day-to-day, let us build a cluster, run the model, and have it go away works. There is a trigger. This top trigger is effectively, time of day. And it says, yep, go out and create the cluster that we want so that it is ready to go when the model is ready to go. And that's sort of down below. The trigger on the bottom row is the files you need to initialize the model are now available wherever, FTP, nomads. So, they exist. So go download them, do the things you need to do. So effectively, the download process of having all of the data you need to start the model and the process of creating the cluster come together at the same time. So you have the data, you have the compute you need, do it, and then when it's all done, delete itself. That's of course a big part, because you don't want this thing to be lying around for hours, not necessarily being of any value to you. So AWS Parallel Cluster, the one we use, definitely orchestrates the spin up, spin down of the cluster resources. The model itself, compiled using Intel's Parallel Studio XE compiler environment, 2020 update number 1. And that was optimal for our setup. All of this was on the Amazon Linux 2 operating system, and the interconnect, EFA is really what we go with. Although you can make a case for TCP. I mean, if you were doing compute jobs where you didn't have a lot of interconnect, like if you're doing 10,000 very low resolution ensemble members, stuff where the number of compute cores is around 100. Well, then, there's not all that much communication going back and forth. And so you could back down to TCP in those instances. So this is the setup, and it's a little bit old. Again, being proprietary nature, I didn't put the latest up here. The bottom row is the NCEP one. When it runs in operations, takes about 100 minutes. They use 1776. I remember that because, of course, that's the the Declaration of Independence and whatnot was that year. 24 cores per instance. Up above is our 2 setups that we run. We have our effectively production run. And the thing about that makes it the production run as opposed to the backup is the column on the far right, the interconnect, which is which is 100 Gbps. The TCP is the 25. So the one on the top, this is what we do. 100. Oh, sorry about that. I bumped that on accident. We have a total core count of 5616, which you can see is larger than what's used in production. All the other details, the number of OMP threads, etc., the type of instance that we use to do the compute. And so, yeah, it is possible using cloud computing resources to acquire more compute than is used by other folks. And if you've got more compute and you've got a model that is reasonably scalable at the core counts that I've listed there, you can actually absolutely go faster. In all of this, and this is where I'm going to get into this in a little bit, the cost thing. Yes, we can do this, but it's not, we didn't have to buy a 156 node cluster and have it in our basement. We just have it for like an hour or 2 per day, whatever it takes to do the run. Well, in this case, it's maybe a little bit less than an hour a day, maybe 40 minutes. And that's the trade-off, that we have this large amount of compute when we need it, and then we don't when we don't. Is cloud really cheaper? And in the case that I just presented, it certainly was. I mean, to get just 100 nodes, 200 nodes, they cost, if you want to pay on-demand pricing, it's maybe $4 per hour per node. So it's like, yeah, it's maybe, I don't know, a few $100s, maybe $1,000 to do one single run. This case is even more interesting to me. This is sort of in the framework of if you wanted to do a reanalysis project of some sort, we needed 10 million core hours. One of the things about cloud computing is, yeah, if you want the compute absolutely, no questions asked, on demand, it does cost maybe $4 an hour for a certain type of core. But there's this thing called the spot market, which is a great deal less. And that's the side that I've got up before, where I just picked one type. Well, actually, I picked the same type that I'd used in the previous slide, so there was some consistency. And it's 69 cents for one node, 36 compute cores for 1 hour. So if I had some project that needed 10 million core hours, I guess that's, you can translate that back into, core days or even model runs. If I wanted that much, and I was able to do it in spot market pricing, which is actually quite common, I definitely use that pricing model if I'm doing some development, trying some new physics or whatnot in the model. You can get 10 million core hours for around $250,000. Again, with all those things listed before. And I know that if I wanted 10 million core hours, if I wanted to buy a machine and I wanted that number of core hours, I don't think I could do that for $250,000. I believe, when you see the prices of some of the new machines going in at various big institutions, I don't think I could do that. I really don't think that I could. And part of it is, of course, because then I get rid of it. I don't keep it in perpetuity. So certainly the price is really, it does work out, the cloud computing. Again, if you have these things where you don't use it all the time, it's a sensible way to go. Though there is some threshold where if you're running everything all the time, that you would be better off just having it yourself. One thing that we did, because, well, it's just sort of what I do, is a case study on performance. We tried a number of different configurations of the cluster just to see, you know, how does FV3 GFS scale in the cloud. We would run it on as few as 252 compute cores to well over 10,000. And each one of those basically went through the process that I outlined a slide or two ago, where you have, you know, the functions that do the job of putting the cluster together. Currently, you know, on the slide a few before, we run the C5 versus C5N. The N means it's got the fast interconnect. 24 of the case study, we use the EFA. The others, we use just the TCP. In every instance of how we developed the compute, 14 terabyte file system was stuck on the side of things to handle all the data that we need to go in and out. This is an example of the sort of things that we were able to achieve in the case study. I mean, there's one of my co-authors, Stefan, Dr. Soselsky, gave a presentation on this, and it's got a number of slides, and I'm not going to go through it. But these are the things that I think a lot of folks that are familiar here at Multicore with, you look at things like this, you know, the time spent in dynamics, radiation physics. Obviously, as you get ever more parallelism, you get this overhead that, you know, sort of there's a trade-off there. But we tried these different OMP number of threads, and we got these different results of this case study. And then this is just, you know, the total wall clock time. The bar on the far left is, of course, the least number of compute cores, the 252 cores. And then as you go progressively farther to the right, you get the higher core counts. The little numbers on the bottom is the layout of the grids. This is something that is not revolutionary, you know, the idea of scaling. I like that, you know, between the second and the third bar, there is this, even though I've got more cores, there's a change, because as we know, there's differences in efficiency with the layouts of a model when it's set, you know, how it distributes the MPI tasks. But this does show about what you would expect to see with scalability. Certainly it's, you know, there's a dependency on the MPI and the OMP threading. We've got 36 cores per node, and so how you divide those things up makes a difference. The thing in all of this, and this is just sort of the amount of time spent on the different components, the thing about this work that was significant to me from the point of view of just using the cloud is that you can see below there are all those different configurations. We did not ever buy that, you know, the machine that does the 11,232 core count on the end. This was all spun up, spun down, and that was it. We never had to buy this thing. And that's, again, one of the values of cloud computing is you can temporarily have a large compute capability without having to buy that for the span of the hardware. So moving on through Brian's 6 questions. On the software side, different companies adopt different, excuse me, I blocked my own screen, different software. Why? Part of that, the different software and the reasons why, is what each company is most familiar with. In the case of where I am at, Maxar, before I was here, absolutely had a strong working relationship with Amazon, AWS. And so that familiarity is the main reason that we went in the direction we did. With everything, it seems, people have their areas of expertise, and this was the one that, you know, we had, and so that's the direction that we worked with. Is performance that much of a concern? The answer is most certainly yes. When I started the presentation a while back, I gave the basic framework that the idea is that, you know, in the case of our things, like, well, yeah, people want to know what the GFS is going to say before everybody else sees it. And so suddenly, if there was just a day where the performance wasn't there, or for some reason, either we had a bad interconnect or who knows what, and we didn't go as fast as we expected, oh my goodness, I mean, the customers would be quite upset about that. I mean, you could imagine that if you had a product that was unreliable, that, you know, one day you're faster, the next you're not, you would eventually not have any customers because there's sort of the reliability is part of what they want. It's absolutely true. And I remember this is actually something that was told to me when I was at Jupiter, was that speed wins. That, yeah, if you can be the fastest in a number of ways, either with that single daily product or just in general with anything, that being the first to market really does give you an advantage. Now, that works for both the real-time daily forecast as well as, yeah, I mean, that bit about the 10 million core hours that I had earlier. Well, you could do that faster in the cloud than you could in an on-prem, I mean, unless you bought an amazingly large on-premises, but that would be just cost prohibitive. And so speed wins, but then cost wins. I mean, that's absolutely the truth in that, you know, there is a bottom line to all of this. And so as noted before, making use of, you know, having the cluster only for the amount of time per day you need it as opposed to always, having it either bursting to scale up for a brief period of time and then going away, both of those works. And of course, there's really no overhead, maintenance, security, power costs. But that's all, wherever these things are, that's on Amazon to do. I mean, it's baked into the cost of the what you pay per node, but that's something that, you know, is spread out between everybody that's buying in. So yeah, if our performance would unexpectedly fall off, or if somebody else, some other company somewhere were to pass us, well, performance is absolutely a concern, because if people are paying you to do something faster or less expensive than others, you really need to make that happen. And this is where, you know, the bit of the reliability of the performance really steps in. When I first started doing cloud computing, I was at Jupiter, and the idea was to do thousands of simulations, but every simulation was relatively small, like a one node kind of effort. And so if you had like, you know, 10,000 runs of a model, but each was only using one node. If one node failed somewhere, you would just say, oh, well, I'll put this into the queue and then it'll just show up later. That, you know, one of them will be a little bit later than the rest. But in doing something that involves MPI, it's like, well, if one of the nodes fails, then the whole thing stops. And certainly in the case of, you know, what we do, if we just sort of had, I mean, that would just be it. You know, there would just be no, if we lost one node mid-run, then that run just would not happen. So the issue then becomes, what are the most cost-effective ways of handling fault tolerance? And the issue there is, well, I mean, yeah, one way to handle it is to have an entirely second full cluster doing the same thing. I think NOAA does this, that there's always two running in two separate locations. But, well, that, you know, in the world of cloud, that means you've doubled your expense. Like, well, if one node fails, I really only need one more to replace it, cost-wise, as opposed to another 200. So are there different ways that you can do this to handle fault tolerance, so that if you do lose one node, you can get back and going relatively quickly and not so expensively? Another thing that is true in cloud computing that's not the same as with on-premises. I mean, I mentioned that, you know, and NOAA has many different computing facilities. Well, so does the cloud, and some of them cost more than others. Some of them have higher demand than others. Like right now, you know, there's cloud computing capability in India that exists, and it's the middle of the night. So, you know, when you're deciding how you want to use your cloud resources, having a way of saying, well, all right, for certain things I want to use not just, you know, off times, evenings and weekends, but maybe off locations to get a little bit more value. I mean, if it's the same kind of processor, then why not? Deeper dive into I/O. This is something that is quite true. I mean, many of you know of this from running MWP applications. I mean, I've definitely seen the NOAA has been working on FE3's latest update, version 16. And in that, they effectively or nearly doubled the number of vertical levels, which means that they doubled the amount of data that they're having to write to disk. And that, the write to disk, when they were doing the NEMS IO format, I think was taking longer than the compute part. That it's like the IO was just, it's like it was, and they got the writer nodes. You know, FE3 has that, IFS from ECMWF has that. But yeah, I mean, if you want to make the speed of your application wall clock time go down, all of it has to be faster. You can't have fast compute and slow IO. And so there are issues that we're going to have to contend with that. One is certainly that when I think of folks that want output of models, different weather forecasting groups out there, they normally don't want the entirety of the NEMS.io files in the case of FE3. That's like, oh yes, just give us GRIB files that have a subset. And so that becomes in cloud, it's like, well, since you have these different options for file system and different options for storage, either something that's either a little easier to access or something, more akin to a tape drive. It's not, but it's it's just a reasonable metaphor that, how to make best use of those things. And then in all of this, given how much data is being produced, how would you want folks to interact with it? I mean, one of the old adages, it was Mark Gavett that sort of was the first person to say this to me, but it's not necessarily his quote, that, yeah, moving data is the thing you want to try to minimize doing. And so, instead of having a bunch of folks download data from a model run, is it more effective to have them go to a set of compute nodes for processing data that are already connected to it? Is accuracy more important for a private sector company using cloud? The answer is, well, what we're doing is we're trying to make sure that we run it as NCEP does. Now, accuracy, though, that's not like a simple goal. I mean, once I have decided to run a model on a different set of hardware, maybe even different compiler options. I mean, certainly if I do, O3 optimization, there's no way I'm going to get back a bitwise reproducible result. It's just not going to happen. Once I've made those changes, it just won't. So, when you say accuracy, it's going to come down to, well, what is your definition of accurate? I use the little quote there, as accurate as possible. You just have to make, what you'll have to do is you'll have to convince yourself that what you've done is in fact all correct and that you haven't introduced any sort of bugs or any sort of thing. So you'd need a number of unit regression tests along the way to confirm that, oh yes, every step along the road is doing what you would expect within a certain tolerance. And so, we're gonna have to, when it comes down to accuracy being more important, we're gonna need to sort of come up with, well, what does that mean? And what is close enough? Like, ECMWF, Tim Palmer working with them on the idea of using single precision rather than double precision values in a forecast ensemble, and saying, well, yes, that, the ensemble results that you get, the collection of runs, it's different. Each one is, but when you put them all together, it's about the same. So yeah, accuracy in the framework of matching NCEP to within some bound, some limit, it does matter. But it also, we have to be dependable and resilient. So, the question that was posed, is accuracy more important? It's like, well, it's not more important or less important. It is important. Let's see. This is the 6th question that Brian put in. Are companies adding, quote, secret sauce to make it, quote, better? In the talk, and I think you've probably gleaned it by now, is it better? There's a lot of different ways that can be obtained. Yeah, there's the speed, just going faster. Skill, you're having a forecast that is more accurate. There is transforming, creating output that is specific to a certain industry. And it really, what better is, depends totally on the person using the output of the model, what their requirements are. There are absolutely companies that are out there that are trying to make a model that's better than everybody else. There is an unnamed company that is basically, they've got these satellites that generate data. And so the idea is that they've got a modeling framework, and then they run it with the addition of their own satellite data, with the idea to producing a better forecast. And from the point of view of some of the customers in weather that I've interacted with, and also with the Forecasters National Weather Service, because the Weather Service office, it's in the same building, it's in the same NOAA building in Boulder, where I worked a few years back. Unless you made a model that was better every single day, it just becomes another model to look at. And so, yeah, there's definitely an idea of having a more accurate forecast, but I don't know yet that anybody's done it consistently. Now, there is a thing about, having something that is unique. There's another unnamed company. They're running a global model at 3-kilometer resolution. And that is something that nobody else is yet doing. The operational centers, NOAA, ECMWF, UK Met Office, they're all around 12-kilometer resolution. Now, so 3 kilometers, that is a unique thing. Of course, they only go out about a day, as opposed to the 16-day forecasts that you would get from NOAA or ECMWF. They're medium, they're global models. But that also makes it a little bit easier. If you're only trying to go out a day rather than 16, there's a bit about what are you going with respect to real-time wall clock. And that's a lower threshold to reach. So while the secret sauce can be unique observations or higher resolution, it can also just be the speed of the computing. In trying to sort of say, where are we going into the future, there are some issues that are going to address. One is portability. We have to, everything that we've done has been sort of unique to our application. And if we wanted to just up and move to an entirely different chipset, it would be great to containerize it, but when you do that, you lose optimization. And so that's something that we will have to address for continuing cloud usage. The cloud, it does change a lot, it changes frequently. And so you need to be able to do that. Capacity, that's one where, if the person that you are trying to be faster than increases its compute, we got to do the same thing. Adaptability, definitely, if there's some new chipset that comes out, and that's the thing that allows you to maintain a speed advantage, then you've got to be able to do it. I mean, the first thing that I talked about was basically lift and shift. Take this thing as it was set up and it was in the repository at NOAA and run it in the cloud. Cloudification is something that's really important for cloud usage. Lift and shift, which I just sort of commented on, it's like, well, that's sort of treating the whole process as if you've got your own cluster somewhere for an hour. But the cloud, with its distributed resources, offers opportunities to do things differently than, this is our setup and it's one thing in one place. You'll have to get a little bit of guidance to do that. You'll work with your vendor, but there is a flexibility that the cloud offers that can only really be attended to if you keep up with it. Places we could go with cloud that would likely be faster than an on-premises. I remember way back, when I was at NOAA, there was just sort of the first workings with GPU accelerators. You had to find them so that you could be able to test stuff on them. In the cloud, they show up very quickly. And I know that there's the tensor processor unit that has shown up. And I couldn't help but notice, I was at supercomputing back in November. It was easy enough to go to. It was in Denver and I live nearby. And seeing how the tensor processor units are really well adapted for matrix operation, certainly matrix multiplication, and knowing how much the data assimilation part of running a model end-to-end uses that, well, maybe, somebody gets a few tensor processor units in their cloud environment sooner than is available in an existing on-premises cluster, and you could do some tests. You could certainly do some work beyond just running the model. You have all this data coming out, and I know the cloud is very adept at being something that can be used to apply machine learning. You've got terabytes, find what matters. Cloudification of the run, and that's the thing that I hinted on the slide before, but because it's so distributed, you could just say, well, all right, I'm going to have a cluster, but the cluster will not consist of 100 nodes of the same thing. It's like, well, give me 100 of Skylakes and 20 with GPU accelerators and maybe a few tensor processors. And then of course, you find the places in the code that are more amenable to using these different types of hardwares, and there you go. And that's something that's more possible in the cloud than it is with an on-premises, because on the cloud, you can kind of try something. If it doesn't work, you don't own it for years. Whereas, with an on-premises, you kind of do. And then just the cloudification task ensembles. I mentioned earlier in the talk that, the resources of cloud computing are distributed all over the place. There's no reason that, if I want to run a 100-member ensemble, that all 100 have to be in the same, server farm somewhere. I could have half of them here, half of them in Europe, or a third here, a third of Europe, and a third in Asia. And that's a different thing. I don't need all of my compute in one location for an ensemble, because it is itself something that can be parallelized. So what it's going to take to get there, definitely, there's going to have to be the software that is required to make the hardware do what we want to do. In the example, and I recognize it's nearly 8:45, so I'm going to not do all the details. But like if I am doing this thing where I'm running a bunch of ensembles in different spots all around the world, well, at some point I'm going to want to make an ensemble mean. So how do I get all that data in the same place? What's the way to do that? Recoding is something that we may be having to do. There's a group in Seattle, okay, an unnamed group in Seattle that's been using grid tools for Python, actually redoing some of FV3 in Python to try and make it more adaptable to different hardwares. Flexibility, I mean, in all of this, advances in cloud computing, very, very fast. You know, there's always an announcement of some new chipset available, it seems every half a year, which is great because you're always able to sort of move forward, but that means you always have to move forward. For us, going back to Maxar, I mentioned before that, that we were running the model, the deterministic GFS. Well, they've upgraded the ensemble this month. And so let's give that a go. That's why the target is up there. This will be actually maybe something that's better on cloud computing than what we've done so far because we can distribute it more. I don't need to have one monster allocation in one site, but I can have them spread out a bit. Further down the road, just in summarizing all that I have said to this point, compared to running when I was at NOAA, and there were these systems that were bought and they were just sort of there for 4 years, the change of the hardware changes are much more rapid. The new processor interconnect, all of it just show up. Every few months it seems some new offering is there. And that's different. And so if you're going to be running NWP in the cloud, yay for that constant improvement and giving you things to do, but you just got to stay on top of it because someone else will. Another thing is, when I thought of cloud computing, it has this notion of being semi-disposable. The bit about, when I was at Jupiter, you run 10,000 single node jobs, and if one of them fails, well then fine, you just submit again and it'll be done later. And that's something that down the road we're going to have to handle. If you ever wanted to use cloud NWP, in a very operational sense, you'd really want to do some work on fault tolerance to make sure that if one node goes down, you're not down for very long. You can come back rather quickly. Maybe some memory map of what's going on that can be stored. I do think that cloud offers some opportunities that don't exist necessarily. Like when I was way back when I was at Penn State, a lot of the work that I did was targeted observations. The idea that a hurricane is coming, send out the hurricane hunters because this is important. We need more data than we normally do. You could do the same thing for modeling. If you're running in the cloud and you're in a hurricane is coming, and you've got your ensemble of forecasts, maybe there's 30 of them. Well, with cloud, you say, well, for a few days, I'm going to do 50 of them because I can and because it's important. And that's something that cloud offers, that scalability. Again, targeted observations, why not targeted modeling? Another difference being the change of pace and how you handle that. And of course, the main point of cloud is to not pay for resources that you don't need. And so in running FV3, and I do know now that I'm approaching the end of the time that I've got to speak in this presentation mode, I definitely know that when you run the model, depending on how you split up the compute, you don't use all of the memory that's available on a compute core. And so, knowing that memory and speed, etc., is part of the costs, well, in the way that I've seen operational centers work with vendors to try and optimize what they get, it seems as though you could do the same thing in the cloud to say, hey, folks, for what we do, this would be a very nice configuration. Additionally, for most of my career, when it comes to HPC and exascale, it's always been one big thing, not distributed. So how to make that mental switch. I have a bit, but it's like when I first learned C, I was writing Fortran in C. There's a similar mental block, well, not block, but hurdle. Obviously, in all of this, we want to limit the amount of data that has to be moved and then limiting how far it has to be moved. When you're using an on-premises, cluster in the basement, it's like, well, it's not only going to stay in the basement, but when you're using the cloud, you've got to be more efficient at it. You do things at runtime. When you do when you do a submit, either with the Slurm or whatnot, you have a node list. And maybe you need to do some work to make a node list every time you do it so that the nodes that are doing the most communicating to each other are the ones that have the shortest air quote distance to go. And that's some of the comments before, how we handle the MPI. And then in all of this is, well, how long is Fortran going to be the way to do things? I recognize that it's a legacy, but in some cases to make best use of what's available, I might have to think about it. I've presented as best as I can what I've done. There's a number of things, just blog posts. You can see these things, the HPC Wire article, the case study. In fact, the good folks at Amazon gave us the award this year, Best HPC Solution for the Public Sector, for the work that we've done on running the model on the cloud. And there was there was a presentation, one of our folks, Travis Hartman, and one of the folks from NOAA, VJ, gave a combined talk on that. That is the conclusion of the presentation of through the slide deck. I've left myself about 10 minutes, I believe, for the questions and answers, and will gladly go through them now. And in fact, I am now looking upon them. So let's see. Oh, wait. Oh, actually, they've just shown up on the screen. I had them on the side before. So let's see. I'm going to start at the top. And the first one is from Paul. If you spin your cluster up and down on demand, how do you know that the resources you need are going to be available when you're ready to run? The answer to that question, Paul, is you sort of don't. Now, one of the things that is true is that you do know what capacity different areas have. And you can certainly ask your vendor where the availability is there. But there are no guarantees. Some days it is there, some days it is not. If it is not, then you would probably need to find a different location that has resources available. This thing where there's compute resources all across the country kind of thing. Well, if it doesn't exist in one place, definitely try another. You definitely don't know for sure, but you definitely can develop a familiarity. Like you try one, like if you really want to have 100 nodes every day at 9 a.m. Mountain Time or some such thing. Well, you try that, and day after day, if it works, then you develop a confidence that it will be there. But in truth, you cannot guarantee it. And so you do need to have perhaps built into whatever framework we're using, the idea that, oh, I have just now tried to spin up my cluster in location A. I only have half of what I need. Let us move on to cluster B or location B instead. So that is the answer that I will offer to Paul's question. John says, why would the use of derived types be an issue in the cloud? The Intel compiler has supported derived types for years. The answer to that question, John, is I wish I remembered. I do remember that I was compiling FV3, and for whatever reason, the compiler that we were using at that time was tripping up. I mean, it was beyond giving warnings. It was just saying, I'm not going to go any further because you have undefined derived types. And I thought it was something that also had to do with its hooking into ESMF. And I'm so apologetic because it was over a year ago that I did that. And I, at the moment, cannot remember, but there were absolutely it was more that there were undefined derived types, or they were leaning on something else. Like it wasn't the information of what it wasn't getting all the way to that spot, that routine. Oh, I'm so sorry. I'll see if I can remind myself what is the case there. So sorry, John. That is my answer to John's question, which is wholly unsatisfying. Tim says, what initial conditions do you use to make sure you are faster than NOAA? On the initial conditions to run FV3 as well as the FV3 ensemble, they're on NOAA's FTP site. I believe for the deterministic run, the single run, there are two files. They are NEMS.io files. One is surface something or the other .nems.io, and the other is ATM, ATM ANL blah, 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 NEMS.io. And those files are posted at, I mean, they just come out with the rest of the file. Now, admittedly, the last few days after they NOAA did the hardware, the Ensemble upgrade, and they have a lot more data to pump out. There's been a little bit of, maybe make a few minutes longer. But effectively, the NEMS.io files are available routinely on the FTP site for the deterministic run. And then there's the collection of tile files, GFS data tiles 1 through 6, surface data 1 through 6, that are available for all the ensemble perturbations should you wish to go that route. And then if you're interested in running at a lower resolution or some such thing, in addition to FE3, there's a set of code called change res that you can use if you want to make things coarser or not. So anyway, that's the source, Tim, of the initial conditions data that we get from NOAA. And then let's see, next up is Brian Flint with a double header. It depends on machine availability. Is there a concern required nodes in the clouds will not be available? Well, there is most certainly a concern that they will not be available. And so you absolutely have to engineer yourself a system that says, well, if I cannot get them in location A, then I better go look in location B or location C. I will say that we have been doing this, let us run the model every day thing for a year now. And I can maybe only one time were we unable to actually get resources to do it. Now, one of the things in that is that, you sort of bake into it the speed. In the slide that I showed way back, I showed that, NOAA took 100 minutes and our best setup took 40. Well, if I only get 2/3 of the nodes, then it runs in 60 minutes, not 40, and it's still faster. So you kind of try to give yourself some wiggle room such that, you do the thing where you try different availability zones within your vendor's cloud resources. And then you say, well, I've got these options I can use. Should I not be able to, maybe you say, well, I can't get the nodes that have the fast interconnect, but I can get the ones that just use TCP. Well, fine, I'll use the TCP ones and it'll be slower, but it'll still get done in time. So that, Mr. Flint, is the answer to, is there a concern? Yes, there is a concern, and you have to be smart about what you do. Next Flint question, can you say something about the people hours required to get code running on cloud versus your own hardware? Boy, that's a really good one. When I think of my own hardware, the only analogy I can think of is when I was at NOAA. And the thing there is that, somebody had already done it. So it wasn't really that big a deal for me to get something to run on Theia or whatnot. To get it to run in the cloud, I will say that the group that I am part with at Maxar, it's not like dozens of people that did this. It was, just a few. And it wasn't, different people have expertise in different things. I definitely knew the model pretty well and the Fortran. Others are, more skilled on the cloud computing aspects. Boy, I don't know. People hours required to get code running up. People hours. I'm not sure that I would know exactly. And I have a feeling that even if I did, I probably, for proprietary reasons, shouldn't necessarily say it. But it's on the, it wasn't the matter. It was a little bit more than a couple of days, but certainly less than a couple of months for our relatively small team. So off with that and on to the question from Todd. Could you talk about whether you end up with busts? Well, here's the thing. The answer is it would happen from time to time, wouldn't it? Once you have switched to a different set of compiler flags, etc., and even things regarding the model itself and the initialization process, you will get different answers. Normally, we don't. There are certainly days where they can be different. Historically, I've found that with just global models, moments where you have like recurving tropical cyclones because they make such a difference on the mid-latitude storm track are times in which you can be more different. Wildly different. sometimes, but it's often, even that, it's like, it can be very localized. Like when I think of the recurving tropical storm analogy, you know, you've got something in the Atlantic, you then might end up pretty different from NOAA in Europe, because that's downstream of that effect, but everything else isn't that different. So I'll say, yeah, I mean, you can definitely be different. And we do keep a track of it. You know, we definitely have automated software that's like, you know, how well do we match various, you know, temperature and pressure and precipitation and whatnot. So it is possible to deviate a bit, but that's fairly rare. But there are definitely different atmospheric regimes that it's more common than others. So that is my answer to Todd's question, which gets me to the last one on the list from Dom. And Dom's final part of his question, which is about that derived types, where he says, excuse me, I shouldn't say he, I do not know if Dom, I should just say Dom and not give a pronoun. The last bit is not sure what went wrong. I fully agree. I mean, it was a year ago and I do not quite remember. I certainly know that I did have to go in and do a few things, and I do believe it was passing information of what the characteristics of the derived type were into or out of like FV3 to ESMF. But I can also tell you that that was so long ago, I can't even remember. I mean, I might have been using that. I think there was definitely some things I can remember going back and forth with, where like I was, at some point I think I was using ESMF3 or some such thing, and I was so far behind that I remember moving forward and certain problems going away. So yes, not sure what went wrong is a completely correct question and answer in this case. I've seen that my clock has hit 9, and that's the last question, and that's the answer to it. So I think that will be that.